Welcome to the Deep Dive, where we plunge into your sources, pull out the most valuable insights, and make sure you walk away well-informed and maybe even a little surprised.
Hope so.
Today, we're tackling a really fascinating new study. It gives us probably the clearest look yet at GPT-5's capabilities in, well, the pretty demanding world of advanced mathematics. Forget the viral posts about it solving basic algebra homework, right? This deep dive is about what happens when AI takes on real cutting-edge research problems. We're looking at excerpts from GPT-5 Mathematics, a quantitative experiment by ASMAT just published.
Fresh off the press.
Exactly. And our mission for you today is to understand if AI can move beyond just, recognizing patterns. Can it genuinely contribute to complex mathematical proofs?
That's the big question.
Can help us go from simply saying this converges, things get closer together, to actually providing this converges at this specific rate. And crucially, why that distinction, that difference between a vague it works and a precise here's how well it works.
Yeah.
Why that's so important.
It really is the core issue here.
Okay, so let's unpack this. The main idea behind this experiment wasn't about simple calculations. It wasn't even just complex symbolic algebra.
Oh, not at all.
It was about pushing GPT-5 to tackle something much more profound, taking a qualitative mathematical theorem, one that just states something exists, and turning it into a quantitative one that gives us an actual measurement.
And what's truly fascinating, I think, is the deliberate choice of battleground. The authors picked a very specific, very challenging area, the intersection of Malliavin calculus and Stein's method.
Okay, whoa, those names. Malliavin calculus, Stein's method.
Yeah.
They sound pretty advanced, maybe a little intimidating.
They are advanced tools, absolutely. But before you get bogged down in the names, the underlying question was elegantly simple. It was, can GPT-5 provide an explicit, measurable rate of convergence for a theorem we already know is true qualitatively?
Okay.
And just as importantly, can that result then stand up to rigorous proof checking by human experts? That's the real test.
That's what separates, as you said, the clever pattern matching from genuine research insight. So, with that ambitious goal, how did they set this challenge up for GPT-5? What was the actual proving ground, so to speak?
Well, they focused on a framework they knew really well, inside out, the Malliavin and Stein approach for central limit theorems.
Okay.
So imagine you have a general statement, that qualitative result that says, basically, this complex random system eventually settles down and looks like a nice, predictable bell curve, a Gaussian.
Right, the classic bell curve.
The authors then challenged GPT-5 to refine that. They asked it to produce a quantitative refinement in what's called total variation distance.
Total variation distance. Okay, that sounds technical again. For those of us not living and breathing this stuff, how should we think about that? What does it measure?
Think of it like this. Instead of just saying, these two shapes look similar, total variation distance gives you a hard number. It says how similar. It's a precise way to measure the maximum difference in probability between two distributions over all possible events.
Gotcha. So it quantifies the closeness.
Exactly. So for this experiment, they wanted GPT-5 to give an explicit numerical bound on how close a specific normalized random variable is to a true Gaussian, a perfect bell curve.
And that requires more than just plugging numbers in.
Oh, absolutely. It requires the AI to reason across intricate definitions, complex identities, something called parity constraints, basically rules about symmetry. It's the kind of careful, nuanced thinking that really puts its mathematical ability to the test.
And they chose a specific kind of variable for this test, right? You mentioned a two-chaos sum. Why that particular mathematical object? What made it a good choice?
That's an excellent question. Yes, the specific target was this two-chaos sum. You can sort of imagine it as a random variable built from two different, almost independent random components living in different, let's call them levels of randomness, or Wiener chaoses.
Okay.
This specific structure is crucial because it's designed to make certain complicated terms. These mixed odd moments essentially vanish. They cancel out.
Ah, so it simplifies things.
It simplifies things if you recognize it. It's like building a puzzle, where certain pieces are guaranteed to fit together neatly if you see the pattern. A truly capable AI needs to spot and exploit these inherent symmetries to simplify the problem. That's a sign of real understanding, not just brute force computation.
Okay, so the setup is clever. Now, here's where it gets really interesting, right? The paper says, with careful guidance from the authors, GPT-5 actually reached a quantitative fourth moment theorem for this Gaussian case. This is the big review.
This is the aha moment, exactly, the punchline of the experiment. The result is a remarkably clean, checkable convergence bound.
Give it to us. What's the bound?
It states, The total variation distance between z, that's their 2-chaos sum variable, and n0, the perfect standard Gaussian, is at most the square root of 6 times the fourth cumulant of z.
Okay, fourth cumulant, another term there. Briefly, what's that telling us?
Yeah. Think of cumulants as refined statistical measures related to moments, but they capture information about the shape of a distribution perhaps more cleanly. The fourth cumulant, specifically, measures how peaked or heavy-tailed a distribution is compared to a Gaussian. So this bound connects the distance to the Gaussian shape directly to this measurable property of the variable itself.
So what does this inequality actually mean for, for you listening, whether you're a data scientist, a researcher, maybe just curious about AI's cutting edge?
It's a huge deal, actually. This single inequality takes an abstract existence claim, the idea that something converges and it transforms it into a concrete numerical estimate you can actually check.
It puts a number on it.
Precisely. It anchors AI mathematics in a space where error bars matter, where precision counts. It's a profound shift from just saying, it looks like a bell curve, to saying, it's this close to a bell curve and here's the measure.
Okay, so we've seen a breakthrough moment. Let's dig into the process. What did GPT-5 actually get right? What were its strong suits in tackling this complex proof?
It correctly used a whole suite of sophisticated tools for this Gaussian case. Think of them as the advanced toolkit for this kind of probability theory.
Like what?
Well, the Malliavin derivative, which helps analyze how sensitive random variables are to small changes in the underlying noise. Then there's the Ornstein-Uhlenbeck operator, which is kind of like a smoothing filter in this context. And crucially, the contraction machinery for multiple integrals, which is essential for simplifying complex products of random variables.
So it knew which tools to pick from the toolbox.
It seemed to, yes. And it even managed to decompose a really difficult covariance term that measures how two parts of the variable move together into simpler orthogonal components based on these chaos levels. And it connected everything back to those fourth cumulants and the parity rules we mentioned.
Wow. Okay, so this isn't just pushing a button and getting an answer back. This sounds like structured multi-step reasoning is actually happening.
Absolutely. We're talking about a domain where even tiny algebraic slips, a misplaced sign or factor, can completely invalidate an entire proof. So this demonstrates why AI for mathematics is moving beyond just being a fancy calculator or a solve my homework tool. It's starting to look like something a working researcher could genuinely use. Not to replace their thinking, but definitely to augment it.
But, and there's usually a but, it wasn't all smooth sailing, was it? Where did GPT-5 trip up? Where did the human expertise become absolutely essential?
You're right, it wasn't perfect, far from it on the first pass. On its very first attempt at a key part, the model actually proposed an incorrect formula for a crucial covariance term.
Ouch. What would have happened if they hadn't caught that?
The proof would have just collapsed.
Yeah.
Simple as that. The final bound would have been wrong. This really highlights what the authors call the collaborative loop.
So it's not just about checking the final answer. You have to check the steps along the way, like showing your work in school.
Exactly, but at a much higher level. Once the human authors challenged that specific incorrect step, GPT-5 was able to revise its derivation and produce the correct identity.
Ah, so it could correct itself, but only with a human prompt.
Correct. It shows the AI can, let's say, get to the right conceptual hill and climb most of the way up, but it still has moments where it stumbles on what you might call loose rocks in the argument. It needs that expert guidance.
And there was another example of this, wasn't there? Something about a Poisson extension?
Yes, very similar situation. When they tried to adapt the argument to a related non-Gaussian setting, the Poisson case, the model initially missed a crucial detail.
What was that?
It overlooked the fact that a specific covariance term involving squared quantities must be non-negative. It's a fundamental property.
Something obvious to a human expert, maybe?
Obvious if you're steeped in the literature, yes. And the property was readily available in the papers they'd fed the model. Again, a simple human nudge, basically pointing it to the right equation number in the source material, got it back on track.
It's a powerful illustration, then, of needing that engaged, knowledgeable human in the loop. It's not autonomous research yet.
Not by a long shot. It's collaboration.
Okay, let's talk a bit more about that Poisson case. You said it mirrored the Gaussian analysis, but had an important twist.
Indeed. The Poisson scenario, which involves randomness based on jumps rather than smooth fluctuations, brings in a key difference. Those mixed odd moments we talked about earlier, they don't necessarily vanish here like they did in the Gaussian case.
And that matters. Why?
It matters enormously. The authors presented a version of the theorem that still gives Gaussian convergence for the two-chaos sum, but only under the condition that those tricky mixed odd terms actually fade away as things scale up.
Okay, so it adds a condition.
Right. And critically, to show this condition was necessary, they constructed a really crisp counterexample.
Counterexample. What did that demonstrate about the AI's understanding? Or maybe its limits?
Well, the counterexample itself was human-designed, but it served as a perfect teaching moment about the subtleties involved, subtleties an AI might miss if just generalizing naively.
What did it show?
It showed you could construct a situation where you match the variance, the overall spread, and even the fourth moment related to the peakiness with a Gaussian distribution. So numerically, it looks similar in some ways, but you still fail to get that nice Gaussian limit overall because a lower order moment, the third moment related to skewness, stubbornly refused to disappear. It didn't vanish like it needed to.
So if I'm getting this right, the big takeaway isn't just about matching a few key numbers like variance or kurtosis.
Exactly. That's the crucial insight here. What's the really big takeaway? It's that matching a handful of numerical moments, while important, is not the whole story. The underlying structure of the mathematical problem, the way its different components interact, the symmetries or lack thereof, that is paramount. Structure dictates the limit.
Okay, that's a powerful point. So let's zoom out. What does all this mean for you, the listener? Whether you're a seasoned researcher grappling with complex data, maybe a technical writer trying to explain nuanced results, or perhaps just someone fascinated by where AI is heading.
Well, the study's most useful conclusion, I think, isn't actually a new mathematical fact per se. It's more of a workflow fact.
A workflow fact.
How so? The authors described working with GPT-5 as feeling remarkably like collaborating with a very strong, very capable, but still junior research assistant right at the beginning of a project.
Okay, I can picture that. What does that assistant do well, and where do they need supervision?
Think of it this way. That assistant can absolutely apply known tools, often very quickly. They can combine ideas from different sources you give them, maybe even suggest plausible extensions or variations on a problem. But crucially, that assistant will also make subtle mistakes. Errors in calculation, missed assumptions, maybe misapplying a theorem slightly, things that require immediate checks by someone more experienced.
So if you want AI for math to actually save you time in the long run,
You first have to invest time up front. You need to be incredibly precise in defining terms, reminding the system about critical properties like parity or which terms should vanish, and importantly, asking for intermediate steps like expansions of formulas that you can verify line by line.
that's how it produces real, trustworthy value in a field this rigorous.
That's fundamentally it. It's not magic. It's guided computation and reasoning.
This insight also helps reframe what we might consider the best AI for mathematics, doesn't it?
It really does. It suggests the best model isn't necessarily the one that just spits out the most surprising or clever new lemma completely on its own.
Right, it might be something else.
It might be the one that allows you, the researcher, to steer it effectively. The one that accepts correction gracefully and, importantly, stays consistent with those corrections after you've made edits. It doesn't just revert back to its old mistakes.
And this paper suggests GPT-5 has some of those capabilities.
It convincingly shows GPT-5 can do that, at least in this context. It makes the whole idea of Math GPT feel less like a kind of internet meme and more like a genuinely useful label for a specific kind of AI toolkit.
So connecting this to the bigger picture, there are definite upsides.
Absolutely. There are clear, real gains from this kind of AI collaboration. GPT-5, with guidance, produced a genuinely new quantitative bound and this Poisson analog with its sharp counterexample. These are exactly the kind of verifiable, non-trivial results that many AI skeptics have been asking for.
But there are also, as you said, costs or caveats.
Predictable costs, yes. Every single line of mathematical output still needs careful human verification, period. The model can be highly confident, sound completely convincing, even when a formula is subtly wrong.
And in mathematics, subtly wrong can mean completely useless.
Or worse, misleading. A single misplaced factor, a wrong sign, can invalidate an entire complex argument.
So the implication is if AI-generated mathematics is going to be part of a serious proof submitted for publication,
the process needs to bake in that human review right from the very first draft. It can't be an afterthought.
the study also mentioned a potential downside, an ecosystem risk.
Yes, a really interesting point. They warned about a possible flood of papers that are technically correct, mathematically sound, but maybe only mildly interesting.
How would that happen?
Once models get good enough at assembling sort of incremental extensions of known results on demand, taking theorem A and tweaking it slightly to get theorem A prime, you could see a deluge of these minor variations.
Making it harder for truly original, groundbreaking work to stand out from the noise.
Potentially, yes. It could raise the bar for novelty or make finding truly significant results harder.
So the key then for researchers using these tools
Choose your
is
problems wisely. Focus on areas where the underlying structure resists this kind of easy copying or tweaking. Look for problems where GPT-5's ability to handle complexity or explore variations helps expose real deep insight rather than just repackaging existing mathematical machinery in a slightly different box.
find the problems where AI adds genuine leverage to human creativity.
Exactly. It's about pushing the boundaries of understanding, not just generating more permutations.
Okay, so for those listening who actually write proofs or develop mathematical models, what's the practical lesson here? How should they approach working with a tool like this?
The main lesson seems to be design with constraints. Be incredibly specific. Meaning, give the model the exact mathematical objects you're working with, clearly define the target you're aiming for, like total variation distance, not just closeness. Specify the key identities or theorems you want it to apply.
Don't leave room for ambiguity.
Precisely. Demand, for instance, that it shows you the reduction to fourth cumulants. Require that every single term in the variance calculation is explicitly written out and bounded before it starts using inequalities.
Basically, force it to show its work at a very granular level.
Yes. This is where AI truly shines right now. Handling that meticulous, sometimes tedious bookkeeping, it frees you, the human, to focus your mental energy on the key conceptual turns, the creative leaps, the overall strategy of the proof.
And what about for those who review proofs?
Yeah.
Does this study offer any tips for them, especially if they suspect AI might have been involved?
It offers a new kind of checklist, absolutely. Things to look out for.
Such as?
Be extra vigilant about claims related to parity or symmetry. Scrutinize the steps that bridge different mathematical concepts, like the jump from a Malliavin-based bound to the final total variation distance. Check the indices used in any contraction formulas. Those are easy places for errors to creep in.
Details matter.
Hugely. If you see a comparison between covariance terms, verify that the expansion is happening on the correct chaos orders or levels of randomness. By looking for these specific potential failure points, you'll likely be able to catch the same sorts of missteps the authors caught here, often quite quickly.
It helps sharpen the reviewer's focus.
Definitely. It augments the critical review process itself.
Now, you mentioned earlier that these kinds of quantitative bounds, like the one GPT-5 helped discover, are powerful because they travel well. What does that mean?
It means they're not just confined to the very specific setup of this one experiment, this particular two-chaos sum. The form of the bound, linking distance to a cumulant, can often be adapted and plugged into questions in many different scientific and engineering disciplines.
You give an example?
Sure. Imagine you have a complex simulation or a machine learning model that takes high-dimensional inputs like satellite images or financial data and outputs a single scalar value, maybe a risk score or a climate prediction.
Okay.
Often, you want to know if that output behaves like a normal Gaussian distribution, especially when averaged over many runs or inputs. These total variation bounds provide a concrete way to certify that asymptotic normality, and crucially, to do it with a number, not just a hand-wavy argument or a shrug.
So it gives you more confidence in your model's output.
Much more. It unlocks tighter error bars on your predictions, cleaner comparisons between different models or methods. It gives AI a genuinely credible, rigorous role in the day-to-day work of solving quantitative problems, where almost everything eventually hinges on turning intuition into an inequality you can stand behind and defend.
And the Poisson counterexample you discussed, that's also valuable beyond its specific context.
Absolutely. It vividly shows where structure breaks down. It's such a powerful reminder that simply matching a couple of statistical measures like variance and kurtosis isn't enough to guarantee Gaussian behavior.
You need more than just matching numbers.
You need the right underlying structure. If that third moment, that skewness, continues to persist in the sum, you simply won't get a Gaussian distribution at the end, no matter how well the variance matches. It's a fundamental structural lesson.
And this lesson likely applies elsewhere.
Oh, for sure. This story about fundamental structural requirements, about which moments need to vanish for certain limits to hold, will repeat in many other non-symmetric situations across math, statistics, physics, engineering. It's a crucial thing to keep in mind whenever you ask a future math GPT to generalize this argument. You have to ask, does the essential structure carry over?
Okay, so let's try to wrap this deep dive up. The big question we started with. Can ChatGPT, or more broadly GPT-5 level models, really do math?
Well, like many things, the answer is nuanced, isn't it?
It seems so. For everyday computational needs, maybe simplifying expressions, plotting functions.
For those tasks, the answer seems to be a pretty clear yes, and it's getting impressively fast and capable.
But for the kind of research-grade work we've been discussing, proving new theorems, deriving complex bounds.
There, the answer is more precise. It's something like, yes, with the right prompts and expert checks, GPT-5 can demonstrably help convert a qualitative theorem into a quantitative one. It can help extend results to new settings. It shows a genuine ability to reason through definitions, apply complex identities correctly, and, importantly, course correct when challenged by a human expert.
So the model doesn't replace the mathematician.
Not even close. It accelerates the parts of the research process that reward patience, meticulousness, and structure. The bookkeeping, the exploration of variations, the application of known techniques.
And this should change how we talk about AI and math.
I think it should fundamentally reset the narrative. The headline isn't AI solved an unsolved problem. At least, not from this study.
What is the headline then?
The headline is something more like, AI can help you produce verifiable, bounded results in mathematically complex areas where the machinery is heavy. That's a far more useful and, frankly, more realistic claim.
And it reflects how real science often gets done collaboratively.
Exactly. It reflects how real research teams work, leveraging different strengths.
So what does this imply for the future? For what we should expect from the next generation of AI models aimed at science and math?
Well, it definitely sets a higher bar. When people ask for the best AI for mathematics in the future, they're going to increasingly include criteria like produces traceable, verifiable bounds and can help identify or analyze sharp counterexamples in that definition. It's not just about getting an answer.
It's about the quality and verifiability of the reasoning.
Precisely. And the study also gave us some really practical, concrete examples of prompts that actually worked in guiding GPT-5 effectively in this mathematical context.
Right, those seem super useful. Can you recap a few?
Sure. Things like always stating the exact target bound and the specific distance measure, like total variation distance, not just a vague norm. Naming your mathematical objects clearly, including their properties like parity and chaos order, and explicitly reminding the model which mixed moments are supposed to disappear.
Being directive.
Very directive, demanding a line-by-line decomposition of things like variance before any inequalities are introduced, asking for specific details like the contraction index or chaos order for key identities it uses.
And if you suspect an error.
If you suspect a sign error or a wrong factor, don't just say, that looks wrong. Ask for the relevant line number or equation from the cited source paper to force the model to align itself with the established literature right at that point.
These habits sound like good scientific practice anyway, just applied to interacting with an AI.
They really are. And as the author suggests, these practices make AI mathematics feel less like some kind of opaque magic trick and much more like reproducible, auditable scaffolding.
Which is the only way it can realistically enter serious scientific workflows, right?
Yeah.
It needs to be trustworthy and checkable.
That's the bottom line. Auditability is key.
Okay, so to recap our deep dive.
Right.
This study paints a credible and I think quite exciting path forward for AI and mathematics. It's not about replacing humans, but augmenting them.
Right. It involves choosing problems with inherent structure where AI can genuinely help, using AI specifically to turn qualitative statements into rigorous quantitative ones. And this is the non-negotiable part, keeping humans firmly in the loop, verifying every crucial algebraic step, every logical hinge.
You should expect speed in execution, maybe help exploring known paths, but not necessarily groundbreaking originality in conception, at least not yet.
And approach every single interaction with that critical reviewer's eye right from the very first line of output.
That, as you said, is how AI earns its desk in the lab. It has to prove its reliability.
So, turning it back to you, the listener, what stands out to you about how this kind of AI collaboration might change your approach to complex problems, whether you're in math or a completely different field? How might you envision using an AI as that strong junior assistant?
It's a fascinating question to ponder. And if this deep dive resonated with you, we really encourage you to try it out on your own turf. Pick a known limit theorem or a qualitative result in your domain.
Something you understand well.
Exactly. Then try asking GPT-5, or a similar advanced model, to express the distance to the limit, maybe in total variation, maybe another metric, and to bound that distance in terms of some small interpretable statistic relevant to your field.
And then comes the crucial part.
Then, critically verify everything. Check the assumptions, check the algebraic steps, check the application of theorems, the parities, the contractions, the covariance terms, whatever applies in your context. See if you can replicate the kind of collaborative loop the authors described.
And share what worked and what didn't. Someone else will undoubtedly learn from your prompt engineering, your verification strategies.
Absolutely. And together, maybe we can help push this kind of structured AI reasoning from being a research novelty into becoming standard scientific practice.